But yes, usually there is a symmetry. To answer your question, whenever we see a miracle taking place, there is a symmetry, and that here is the conservation of charge that takes you to word identity that then makes sure that this keeps preserved. But it will take me some time to talk about. What I need to, not to lose the line of thought, I have to talk about masses, particle masses, which means the Higgs mechanism. We have to start speaking how would we test this beautiful thing that says that you and I get the masses. Well, we don't get the mass. Actually, that's not true. That you could read in many popular exposés of the Higgs, right? People used to say you could read New York Times that you know it's this God's particle responsible for our masses. Unfortunately, our masses do not depend on the Higgs, right? Because our masses depend on the proton and neutron mass. Proton and neutron mass is not the Higgs mechanism because they are not elementary particles, proton and neutron. Remember we said a few times. Elementary particle masses, yes, they get a mass from the Higgs mechanism, we are more and more sure, but not the composed states. The mass of the proton is just this crazy dynamics of gluons that do their dance and fog inside. Quarks are practically massless. So what we found for the gauge boson masses, so I need both the masses and the direction that they were very important was the gauge bosons. And we found something like this MWG, W plus, W minus, plus 1/2 G over cosine theta W, mz, z mu h. This ended up being the coupling of W and Z. But there is no factor of 2, it's just the way I'm writing W. This would be 1/2 A1 square plus A2 square. And this would be 1/2 A3 square when I ignore theta W. Okay, it's the same normalization. So maybe I write it, this would be 1/2 G MW A1 square plus A2 square. And don't write the mu index. The same. The mass times the coupling, which is very important. Okay, we had an important information that everything came from V. MW was 1/2 GV. And then there was a raw parameter that said that mz cosine theta W is MW. I will not look at the loops, okay? We are doing everything at 3 levels, so rho is 1. I'm going to look at the fancy corrections, okay? What about the fermions? The fermions get a mass we set from the Yukawa interactions, which look like this. There was QL bar, phi dr, you remember? Doublet. Hypercharges, okay, this is just the definition of my hypercharge of phi. Okay, I took it to be plus 1. What I mean is the following, there is Yukawa up, QL bar, and then this becomes phi tilde, UR. There are people who call this phi and call this phi tilde, it's just relative, what I call left. It's a question of convention, right? These are complex conjugates of each other, particle and antiparticle. This is to have the hypercharge, correct, and then there was Yukawa E, L lepton doublet, phi ER. And of course there is always Hermitian conjugate. Phi is unitary phi, so it's V plus H, and phi theta in the unitary thing is V plus H. Remember there was an I sigma 2 and so on, but it made it lower becomes up. Here I can define. And you can see immediately what happens. What I pick up here is the down quark, you agree? This has a lower component. What I will pick up here is an up quark. What I will pick up here is the lower component. After all, QL was UDL and LL was nu EL. So notice that I get one and the same expression for all the guys. I can write like this. This gives me for every fermion, Yukawa fermion, FL, FR plus Hermitian conjugate times H plus V. S stands for down, up, and electron. It does not stand for neutrino. Notice what happened. I have no such term for neutrino because I wrote the minimal theory, and the minimal theory says you write the fields that exist. There is no right-handed neutrino, I'm told. Okay, 1961, 1967, it will be repeated by Weinberg and Glescher, the idea of Salam to write the minimal, of Glescher, sorry, Weinberg and Salam, the idea of Glescher. So the minimal theory says here I'm getting interaction with the Higgs, but neutrino is notably absent. So the first great prediction of the standard model is the neutrino mass is 0. When the numbers are small, people like to imagine 0, so there was already a strong prejudice that this was 0. And so you imagine the theory says that was emerging as the theory slowly but surely in the 70s, so the prejudice would grow that neutrino is massless. The other guys, immediately this I can write as Yukawa fermion V, F bar F. You see, this is by definition F bar F, right? Where we had our convention that F, there are various ways I write it, F was FL plus FR for us. Left and right were projected states to left and right direction. Okay, with 1 and plus minus gamma 5. Right? So this is just your first homework. The pre-homework. The pre-course.
Why we set it to 0, the mass of the neutrino?
We didn't set it to 0. No, I just wrote everything I could.
But is it like something that essentially you will get from the symmetry breaking, like analogously to now?
Everything is coming from here. I write, or I should have stressed this. What about the others? What about the other plot? Did I give you 2 plots? But you have the other one. You have the other one. It's very strange. So it seems that Patricia printed. Ah, no, there they are. Okay, sorry. The rule, the prescription of renormalizability. If you want to write a good theory, at Hoff taught us, you have to do the following. You write to me your theory. Your theory is defined by the gauge principle that you have chosen. Okay, there is a certain gauge group. Then you choose your fields. Then he says you must write all the interactions consistent with that symmetry. Otherwise you may get infinities, things will not go wrong. And that's what it means, all interactions of dimension 4. Remember we stressed that, and Saif is teaching you, that renormalizable theories have to have interactions of dimension 4. And I will remind you on simple examples, if you wish, as we go along, why the higher dimensions wouldn't work. So if you accept that, I've written the most general potential, I've written the most general gauge couplings, the most general covariant derivative I could with my symmetry. I wrote also the most general Yukawa couplings. So you should think, your question should be, did Goran forget something? If I forget something, maybe then we can say whether I have assumed.
Yeah, but
I've written what I could.
Yes, but I mean, what prevent us just from adding a tail, like the last one with neutrino, right?
Which neutrino? But there is no neutrino, right?
So
why don't I add, what is neutrino right? What is neutrino right? Why, you can add hundreds more fields.
But I mean, in general, like if you just constructing the minimal theory here, in principle, it's not. You can put it in principle mathematically and the normalization.
No, but you can put hundreds of more fields.
Yeah,
no, but how would you choose?
From put it. So
no, wait. Well, you can put hundreds of more fields.
Mm-hmm.
Well, I can put anything you want. I can put a triplet of Higgs. I can put gauge bosons. I'll show you funny gauge bosons. They have quantum numbers which are very unusual, okay? Why didn't I put them? Why do you write the simplest Lagrangian, you are Einstein or Hilbert? Why don't you include other terms? Why, you could. You would have no prediction. You wouldn't know what to choose. So why would you introduce the field in 1961 which nobody has seen? That wouldn't be the minimal theory. I'm not asking you to do the following, which is a cheap exercise which is called model building, and to me is a lousy physics, which is the following. You find the fact, oh, neutrino is massive. Oh, what can I add to the model to get that? This is not how great theories are developed. What we love about theories of nature is when they are introduced to explain a certain phenomenon. Einstein wants to understand deeper the issue of falling bodies. And then he tells you that light also bends. You love that. Because if someone says, oh, look, the light bends, and you say, oh, I will put some terms so that the light bends, but you like theories that structurally predict new phenomena without adding ad hoc fields, interactions, whatever. So when I want to read off the physics of the standard model, I take the structure. I've introduced the theory. Remember what I wanted? I wanted to have a theory of weak interactions, not a theory of particle masses. This is how it all started. And it was a great thing. It's beautiful that you get a prediction. You and I will think what to do when we fail. But first you stick to your prediction. Because this prediction goes with all the other predictions. You understand? For example, you could ask me, why did you take just one Higgs doublet? Why don't you take two? You could. Or three. I would lose all the predictions if I take two. All hell would break loose. So I do once again, well, I didn't do this, okay, but I'm doing it here. I'm using this principle as carefully as far as I can. I've tried to resist an itch of doing model building in my own research because it's too easy. If you want to play a serious game like chess, don't change the rules. It's more fun. If you change the rules, it'll be easier to play. So I want to push to the bitter end all the predictions of the standard model. And then, of course, if somewhere we fail, that will be a window to new physics. But not before. Okay, what do I get here? 1 plus h over v. Agree. You with me? So here is another important prediction. Let me not write these elementary things. That the fermion masses, by fermion now I mean charged fermion, is Yukawa fermion times V. I promise to you that all the masses will have to be proportional to vacuum excitation value. That was the only scale. And I said it will always be an appropriate interaction that will define the mass. Yes, Nicola.
By writing this theory, nobody thought that they are introducing too much free parameters because they are introducing a Yukawa Y for each lepton. But
do you feel like that, or you read it?
I feel
Tell me honestly, you feel like that?
No.
I may. I must admit that my own feelings changed over the time. And there was a time when I had a similar feeling. I don't know whether it was actually my feeling or because everybody else was saying it, okay? There is something which is very dangerous, which is called groupthink, and you will succumb to it. I can guarantee you. You will hear what other people tell you. This is even called the Fermion mass problem. It is so crazy. The people call this a problem because they say, oh, oh, boron or Weinberg, but you cannot predict the electron mass. You have to introduce the parameter. Did you ever predict any mass before? Imagine Einstein gives you a beautiful theory, but you say, oh, but you have to assume the mass of the planet. Kepler spent his life computing distances of the planets from the sun. He was bloody wrong. There is nothing fundamental about that. I remember in the early 80s when I myself got intrigued by this, and I was working, every once again I come back to this issue and try to understand the origin of these Yukawa couplings, okay? You have to be very careful when you say that you want to understand, because instead of understanding, you just may play some trivial mathematical game in which you know, when Einstein says he wants to understand, Einstein was not completely stupid. That's one thing. When you and I say it, we should be careful. In the 80s, I remember Lincoln Wolfenstein, whose name I will mention often, a distinguished physicist. He died. Was telling me, I remember we were spending a term in Santa Barbara on a sabbatical. There were a bunch of us discussing this a lot. There was Frank Wilczek and so on, and we were working together. And among other things, we were working on these issues. And Lincoln was saying, Wolfenstein was saying, that's wrong. You guys are calculating the distances of the planets. And I must say, 40 years later, no progress has been made. So maybe this is not the issue. Then again, maybe it is. So let me first argue, there is absolutely no Fermion mass problem. This could be an issue, it's a very ambitious issue, because what you are asking me immediately as I'm giving you the theory, and that I'm suspicious that it's actually your feeling. I think your feeling may have been influenced by what you've heard other people say. Forgive me for saying that, because I'm giving you a beautiful theory, you're telling me, oh, but I want more than that. You didn't ask me immediately what is MW. You didn't ask me, can you predict theta W? You didn't ask me, can you predict alpha when I give you QED? Imagine you sell Phi, oh, it's great, you guys can compute, but can you predict alpha? Normally you don't do that. This said, I'll come back to it, you say, well, but there are too many, because now there are other generations. If there was just one generation, I could live with that. Maybe. But there is no problem whatsoever. This could be an issue to worry about. Sure, not a problem. I actually want to say something maybe that will surprise you. So I can write this as M fermion, F bar F, 1 plus H over V plus. So why don't I split the interaction? Plus H. And normally I can eliminate this V, you agree? So I will get, actually let me write it nicely, G over 2, M fermion over MW, Higgs F bar F. I mean,
this is why people is studying the coupling between Higgs and the top part, right? So
for example,
you were telling us last lecture.
For example, everything is here. So let me argue, let me try to be very unconventional and say, not only that this is not a problem, let me try to argue that this is beautiful. That this, what should worry you and me, is actually beautiful, because imagine that I don't have this. Then I will have a lot of statical parameters, which is kind of sand, you know, some kind of Mendeleev table I have to relearn about particle masses. There is up quark, down quark, electron, then charm quark, strange quark, and so on and so forth. Then there are mixing angles, which somehow. So in that case, masses would be static parameters, deprived of any interesting physical meaning or dynamics. Here, however, notice, you and I, what we want to do, we claim that there is a Higgs mechanism. This is the essence, so we were taken to this in order to have a theory of weak interactions that is renormalizable, that I can compute. I ended up having to do this. That actually told me much more. Says that particle masses for every particle is appropriate coupling G of that particle times the vacuum expectation value, we can say, for all the standard model particles, you agree. Massive. We would like to check that. So how would I check that? You know, I'm saying that vacuum is full of some kind of ether. You know, the old picture of ether is coming back. But I don't know how to check that because I'm like a fish living in the sea. I don't know that there is something else because, remember I told you I would have to heat up the system so much that I end up through a phase transition in which V goes to 0. The temperature was too large. So what remains to us, the only way to check it, is precisely in this so-called problem. Because it tells me it's true that I don't know why the mass is what it is. Do I really have to know why the numbers are what they are? I don't know. But what I can tell you, you give me this number, I'm Weinberg. I can compute all the decay rates. Give me this number, and I will compute all the Higgs decay rates. And these four, actually these apparently problematic values of these numbers serve a profound role. This is the only way we can check the Higgs mechanism for a long, long time. 50 years, 100 years, 200 years. I don't know where we could reach this phase transition to actually see what is going on. So I would say on the contrary, I want to show you that you and I could understand maybe by and large, without doing calculations, okay, the art would be that, you know, I want to give you a feel what it means to do particle physics. That somehow we try to reproduce these ugly, complicated features without computing. And in order to do that, we have to be able to so I'll give you a homework to do a precise calculation, but you can agree with me immediately from here. I expect, as usual, that the decay rate will be proportional to the coupling square. It's a rate. So I would say mf over mw squared. And then the only scale, fermions are much lighter than the Higgs. So what I expect mh. I'm sure they'll get from phase space something like, you know, 1 minus 4 m fermion square over mh square, something like this. I may get to some power. When the 2m fermion is bigger than mh, they cannot decay. But let's think of our fermions, which are much lighter than the Higgs. You and I know today Higgs is 125 GeV, and the fermions are at most 5 GeV. And top is too heavy, so I don't have to worry about something close, okay? So this is extremely important. So these ugly parameters, apparently, I'm told to worry about them, are a blessing in disguise. It's not a curse. I can now compute every branching ratio, okay? And it's good that there are many of them, because then we will start to believe in the Higgs mechanism. 1 or 2 numbers, we will say, oh, maybe an accident. So this is the first thing. Look at the plot on the decay rates is the first plot.
This one? No.
The other one. The one which has also production rates, the 3 plots. Let's just look at the fermion. Forget the WW. Look at the beginning of the, on the left of the axis. So who is dominant? BB bar. It almost all goes into BB bar. Why don't you take? Almost everything goes into BB bar. You agree? Look at the left. It's and remember that MB, just to get a feel, MB is about 5 GeV and M tau is about 2 GeV. So it's about a factor of 2 in the masses. Actually, it's a little less than 5. So I would expect 2 square 4 times, but I think it's much bigger than 4 times, even 10 times. Why? After all, I should be right. Because everything, you know, I don't compute it, but all the coefficients will be the same. So in principle, okay, if I didn't write G over whatever, okay, or 8 over 8 pi or something, that will be in the other branching ratio. So what is going on? Why is B so much dominant? Something that's very easy to remember, quarks carry color. So there's 3 B quarks. So it's not only that I have a bigger branching ratio, but I can go into 3 B quarks. B red, B yellow, and B blue. So I get a factor of. I don't know what the ratio masses precisely are. I don't want to remember them, okay. So in the beginning, it's all B quark. And then it will go down because something strange will happen. Notice that WW and ZZ will keep growing. And will never go down. And that's sort of strange. So let's try to understand that. Let's do the same thing. Let's not compute. Let's just estimate. Okay? So I have a coupling G, MV, V mu. Let's V be some gauge boson, okay? There is a coupling G, MV, V mu, up to coefficient, times the Higgs. Okay? Which goes in the momentum space G, MV, epsilon mu, Higgs. So what will be the amplitude square? Will be G square MV square, sum epsilon mu star. Let me write epsilon mu star, epsilon mu star. The square, right? There is a dummy index. I have to take a complex conjugate. Okay, this will be the amplitude square, and I should sum over all the polarizations, over all the spins of the gauge boson. I don't want to identify whether it's longitudinal transfer. I just look at the decay of the Higgs, right? Complete guy. Remember this? The polarization tensor for the, we wrote it. Well, it doesn't matter if you don't. This is G square and V square. And then you get minus G mu nu plus K nu over MV square minus G mu nu plus K nu over MV square. But K mu is the momentum that the gauge boson is taking away.
You have H square from the beginning also.
What?
H square. H square.
H is decaying. I'm looking at the amplitude square. There's no H. I'm looking at the amplitude. Not at the, no, this will be an interaction, but saying the amplitude is just the square of the coupling, and then I have to write the polarization tensor. There is no H here. It's a scalar field, right? Remember the Feynman rules. When it's a scalar field, you put 1 where there is a spinner, you have to put your spinner index when there is a gauge field, just to keep the
so
Lorentz.
it's not H also in the upper one.
Higgs is at rest. I'm looking at the decay rate at rest. Okay, they should be boosted if the Higgs moves.
The momentum space up there.
Yeah. This is in the momentum space, right? I shouldn't have put H. Okay. Thank you. He's right. Good. What I want to show you is something very interesting. They were very puzzling that you wouldn't guess immediately, because if you look at the let's look together so that I don't look. If you look at look what happens when the Higgs masses keep increasing. W and W somehow, and ZZ keep dominating everything else. For a while the top quark will show up, right, when you get enough mass to decay into TT bar around 350, 400 GeV, but then it will go down. The thing that will stay somehow is W and Z. So you notice because of that everything else has to go down. We are looking at branching ratios, relative decay rates. Now why? So notice if the Higgs mass is very large. I mean, what would this be? Imagine that M Higgs, just to understand, imagine that M Higgs is much bigger than 2MV. Not a realistic situation. At the end, it's not the world in which we live. I just want to understand the hypothetical heavy Higgs decay rate. What would I get? Which piece would be dominant? Notice that when Higgs is very heavy, then the gauge bosons are practically masses and they take away half of the Higgs mass. So K mu is roughly, the momentum is roughly half of the Higgs mass, which is dominant. So this would go, the dominant piece in this limit would be coming from here. Because I get K squared over MV squared, everything squared. But K squared is MH squared, or half, whatever. For very large, this is of the order MH squared. Gauge bosons are practically masses. They take all the mass of the Higgs as their kinetic energy. It's a factor of half, which I'm not writing. Remember, I didn't write any factors here. Okay, I just want to look at the dependence. So notice an interesting thing. We get G squared. I will get MH to the fourth. No, this is small h. Over MV squared. This is my amplitude. Then, of course, when we write the decay rate, there was 1 over MH. Remember, one of the two energies. Anyway, you can find out dimensionally H going into VV becomes G squared MH cubed over MV squared. When MH is much bigger than MV. We'll have a homework in which actually I will ask you guys to compute this for all the Higgs masses and find the precise form. It's a straightforward calculation, it's here. You will write K mu from the conservation moment. But you see, this has to be of this form. So notice very important thing, it goes as MH cubed. It's very different from the fermion decays. They go as MH. So if the MH keeps increasing, WW and ZZ dominate. And there is an interesting thing that the WW is substantially bigger than ZZ, right? But I don't know how it's plotted at the end. Does it stabilize about? Naively, I would say, what would I say naively if I don't compute? I would say the WW should be twice as big as Z. Because there are two fields in a W. There is A1 and A2. There is W plus and W minus if you wish. There are two fields. It's made out, it's a complex field. It's made out of A1 and A2. So when the Higgs decays into W, decays into A1 and A2. When it decays into Z, decays mostly into A3. Theta W, you can take theta W to be 0 in the first approximation. You don't go very wrong, remember? Sine squared W is relatively small. Just to get a feel. But it's not a factor of 2. I think it's bigger. In the beginning, it's sort of, maybe you can see better than me. In the beginning, the ratio is quite, it's bigger than a factor of 2. The very ZZ. And WW, right, the ratio is bigger than 2, substantially bigger. But later on, maybe it's okay. But it's an interesting thing when they are, you know, in the beginning, you don't decay into two W's. You know what happens, why they write still WW? When the Higgs mass is smaller than two W masses, you'd actually decay into a W and W star. We say one is off shell. You get this process. Higgs decaying into W. This can be on shell. Say W plus, W minus, and then this can decay, for example, into electron and antineutrino or something like this. So we still call it WW, but we should be careful. It's not WW. And some people make a distinction. They put WW star. Star says the particles which are off shell, okay, which you always boost the decay rate when you produce something on shell, okay. because now I'm looking at the three-body states, okay? So there is sort of a little puzzling thing, why is WW so dominant in the beginning? But then I have to do a better calculation so I understand it. When I go to very heavy Higgs, when it decays into 2 Ws, then roughly what I would expect, I think, is true. The WW is about 2 ZZ. Am I right? I don't have my glasses now. So notice that a good deal of this we are reproducing, okay? Without doing any calculations, just thinking about this. You know, this is the famous thing that I told you. Oh, let's try to understand. Before we go into the numbers, let's try to understand that. So, two fundamental formulas. This will be, and this is pretty good estimate. You will see. This is also a pretty good estimate. When Higgs is very big, let's understand these features, although Higgs is not so heavy. Remember when I told you that there is always a problem of a gauge boson mass going to 0. That was a Proca problem. You get divergences. And then I said that the spontaneous symmetry breaking cures it, okay? And we found some examples already before. So let's see how it cures it. Let's try to understand what happens here. Oh, here there is actually a beautiful question hidden. Let me see if you will have. So let's look at this. Gamma Higgs going to VV is proportional, what did I say, G square, MH cube, MV square, when MH is big. And that's what we wanted to understand. We wanted to understand high energy behavior or Yang-Mills theories of the Higgs Yang-Mills theories. We wanted to understand what happens when the energy becomes very large. Energy in this case is the Higgs mass. There is a tremendous available energy, right? Or the limit when the gauge boson mass goes to 0. So notice, if I put mass by hand, MV, I have a problem. If I look at the Proca theory, I have a problem. I get an infinity when MV go to 0 in the Proca theory. But what about the Higgs mechanism theory? Well, remember, MV is GV. But then Higgs is square root of lambda times V. Also, so the V going to 0 limit, I said the only way you can take the limit is V going to 0. This is the scale. This is the parameter that determines everything, all of the physics. So look at that limit when V is small. So what is this proportional to? So gamma H VV anyway is proportional to lambda 3/2 times V. That's a dependence. MH cubed times V. G square cancelled. This is perfectly smooth in the limit V goes to 0. If anything goes to 0, well, the Higgs becomes massless, so it won't decay. Everything is okay. There is no bloody divergence that would worry us. This is one of the ways of saying, believing that this theory is going to be good. There is it's a very soft way of giving masses. It does what we expected. We said when we go to very high energies, the masses should become less important. So we shouldn't get this divergence. So everything is okay. V going to 0 limit, gamma goes to 0. Why? Because MH goes to 0. So particle can decay. That's what I expected. Everything's back to normal. What about G going to 0 limit? It's another interesting limit to look at. What will happen when G goes to 0? will I get? G we cancel, and I will get this again. Am I right? Right? And V is not small. I'm saying, let me look at large V, but G very small. But when G goes to 0, then the gauge boson is not coupled to the Higgs. I raised it, but you remember it. So how can Higgs decay into gauge bosons if it's not coupled to them? Well, that's a bit crazy. What's going on? Where did I go wrong? But let me cite Ken Wilson here. I don't guarantee everything I write on the blackboard, but this I do. In other words, this is correct. What is going on? And that's a beautiful question, not trivial. In other words, how I'm finding that Higgs decay. Forget the fermions. Decouple the fermions. Take your Kawa coupling is equal to 0, take the mass is equal to 0. So don't even worry about the fermions. I'm looking at that case of gauge symmetry, and I'm taking the limit when G goes to 0. What happens when G goes to 0? Who remembers? They are Goldstone bosons. They become physical. You see, when the Higgs is decaying, notice an interesting thing. When the Higgs is decaying into gauge boson, for heavy Higgs is decaying mostly into longitudinal gauge boson. These are the guys that ate the... How did they become longitudinal? They ate those funny guys. Nambu Goldstone bosons. Nambu Goldstone bosons. Says, Salam, can you please call them Nambu Goldstone bosons? So he eats those Nambu Goldstone bosons, W or whoever it is, and becomes heavy. But now, when G goes to 0, there are Goldstone bosons. So the Higgs, of course, will decay into the Goldstone bosons. They actually exist. And remember how the potential looked like? Potential in this limit was lambda over 4. Then there was phi square, which was V plus H plus IG. Let's just write the simplest partner of the Higgs. We can generalize it to more fields. V plus H plus IG. What is this? Square minus V square, everything square, right? No. Why don't I write like this? It's better.
Yeah.
So this is lambda over 4. So this is 2VH plus H square plus V square, everything square. Am I right?
G square.
G square is better. V square cancels, okay, G square doesn't. So the dominant term from here is this one. I'm looking at the terms when the dominant term and I have a single Higgs. So what do I get? These terms, I will get lambda V H G square. Am I right? I think so. Everybody follows me?
Mm-hmm.
So I'm looking at the limit, G going to 0 limit. I can't eat the G guy, it's there. So in other words, from here, I find out that Higgs can decay. I don't know how to draw this. Let me put two lines. I don't know, Nambu Goldstone bosons. Okay, these are G's. Just to show them a little different from H, right? The scalars we do with a scalar line. So this becomes possible, you agree? Manifest. What will be this decay rate? Higgs going to GG is going to be proportional to the square of the coupling, which is lambda square V square No? We have to get the units right. It's going to be proportional to mh. So I'm going to get another square root, sorry, no. This is already of the order v squared, it's the same thing. So it will be cut off by mh, in this case, because the coupling is dimensional, we cannot argue. And that will come in the decay rates. Remember, there was 1 over 2 energy of the initial state, which is mass of the Higgs, divided by the mass of the Higgs. It's a very unusual behavior when the coupling is dimension full. Then you don't go through this naive reasoning as you said here, because here the dimension tells you that the mh would come up, because you'll get mh squared over mh. You will see. Here we found it, a similar thing. We get mh to the fourth, and we got mh cubed. And this notice, and mh is the square root of lambda times v. This goes precisely as lambda 3/2 times v. I recapture the result that I got in the limit v going to 0. Everything is okay. And there is this beauty, this is very important, okay, for you when you're doing calculations here. This is a nice way of checking your results. We have to recapture the Nambu-Goldstone mechanism when the gauge bosons are decoupled, when there is no local symmetry, okay? And this is yet another time when we see that everything is okay. So I'm trying to show you sort of a little art of doing your calculations without computing. Again, you can feel what is going on. It's easy to be wrong in this, okay? This is surely not the complete way of doing it. One has to sit down and compute, but it's always a good idea to know, to expect what you should get. The thing is also that the coefficients which look order 1, sometimes they become large, and therefore to really predict the phenomenon you need to sit down. But you can get a good feel of what is going on. As you can see, we can understand everything without doing the actual calculation. I think now you agree that we understand the decay rates? Well, to a degree. Let's go on a little bit more. There is B, tau. What is below tau? Charm. And then below charm? It's?
Gamma, photons.
No, the photons should be down.
Yeah.
Gamma.
W.
G. What are G's?
What are those G's?
Huh?
What are those gluons?
Gluons. Very good. So let's just say a few words more to really reproduce this diagram. Oh, before I do that, let me ask you, look at the W and Z part. Notice that they are growing. They go as mh cubed, so I'm not surprised that they are growing. But then there is a moment when the Z falls down. Why? And where does it happen? Try to see. You have better eyesight. Around?
160.
You have said 160, very good. What is 160?
2 times the mass.
Of the W. So what happens there? That actually on-shell production of W opened up. At that moment, of course, you want to go into 2 W's on shell. You cannot go into 2 Z's. So Z goes down, then eventually the 2 Z's will open up, and then it will immediately go up like crazy right now. Now it can decay into 2W and 2Z, and then it stabilizes at W being a little more because there are 2 W's. Okay, that roughly we understood. Then notice later on, top quark woke up, Higgs could decay into top quark. No, it woke up suddenly, went into decay, and then it went down. Why? Because W will dominate, because W will go as mh cubed, but the top quark will go as mh. So the fact that you had a large coupling helped you. At some point, you see it's almost as big as the Z. Well, it's heavier, so it loses the phase space. Unfortunately, Higgs is light. If Higgs was very heavy, we would see this beautiful picture of longitudinal W and Z. That would have been really spectacular, which has to do with the Higgs mechanism at best. It would have been even nicer, a heavy Higgs, but life is what it is. So, if you look at the diagram, there is also a little bit low charm. There is Higgs going into gluons. G is gluon. How does that happen? Gluons are massless. This you knew, right? You told me before, it goes through the top quark. So it goes like this. I on purpose wanted to this be very sketchy, okay? Please don't feel bad. This is very important that you compute. It's a beautiful calculation and it gives you a deeper understanding of the Higgs mechanism. It's a kind of must, I would say. You can also do this, but it will turn out that this is very easy. That there is almost nothing to do here. You computed the W decay, which is much less trivial than the scalar decay. So for you, this is a piece, okay. Higgs going into two gauge bosons is not trivial. So we said that Higgs can decay, Higgs can couple to two gluons. Well, then we can do gluons like this to separate them. So this is small g. Some people use capital G. Let's stick to small g because we use capital G for Goldstone bosons. So maybe, okay. I've seen more often. So this is how Higgs, of course, any fermion contributes, but very little unless it's heavy. Because what enters here is the coupling G over 2 M fermion over MW. So what you do, you select the top. By the way, it can also decay into two photons. So I'll just make a comment. Notice the two photons. Maybe I should take my glasses. Maybe Nicolas. Sorry. So this is B.
Which one?
Then I have B, tau.
Yeah. G. It's easy one.
G is which one? Okay.
This one.
And then we have the gamma gamma must be this one. Right. And G grows in the beginning, right? Notice that gamma gamma, okay, Nicolas is helping to see. Gamma gamma, notice that gamma gamma and G are growing. Unlike the fermions which go down, these guys are growing. They will go down eventually. Everybody will go down, you agree, except for W and Z, because eventually those guys will dominate so much that they practically will be all the Higgs goes into WW and ZZ. In the beginning, why do they grow up? Well, in order for Higgs to decay into two gauge bosons, there must be an interaction like this. Now that interaction must be gauge invariant. Okay, if I'm talking about the massless gauge bosons here, gluons and the photon. So to make it simpler, let's talk about the photon. Let's first talk about Higgs gamma gamma interaction. Okay, how could it look? It could look like this, you agree? Let's try it. But can it look like this? It's Lorentz invariant after all. Can it look like this?
No, because it's massless.
It's still gauge boson is mass and there is gauge invariance. If you had a term like this, then you will have a mass term, okay? Then there will be a V. There is always H plus V. So this is forbidden. The way you actually couple this F nu, F nu. And the way couples to G would be G mu nu with the proper Yang-Mills index, but you notice here. So this will be the, by the way, this calculation is doable, it's not easy. I've given it a few times on a take-home.
Nice.
And very few students did it. I think he made a mistake in the end. I thought that Vishari did it completely. Vishari did a great take-home, I must say. Some of the best. We had some. Rarely you get people that tend to do everything. My ex-student Vladimir Tejo did a great. I remember it was 10 years ago. But I think even he made a mistake that we found out later, okay. The tutor didn't see it, okay. We saw it together. Notice, what is the dimension of this? 5. Because this is 4, you know, this is the... So that means that this will be divided by something. The dimension of the Lagrangian is 4, not 5. And that means the largest mass, which is the mass of this particle, which is m top. Something like this will come out, okay? 1 over whatever. But that means when you calculate the rate gamma Higgs going to gamma gamma, say, or GG, there will be the same logic. It's going to be proportional 1 over that m. Presumably m top is the largest mass in the game. Higgs is lighter than the top, so Higgs mass. So that means that m Higgs cube will come out here. Period. It has to be. Dimensional arguments. These guys are massless. Once you have your interaction, you can figure out everything, right? The only scale that remains afterwards when you do the phase space is mass of the Higgs. So this grows. So this is noticed, although they're very small, the gamma gamma and even GG is small, they grow. So we wanted to understand, what I wanted us be able, without doing calculations, that you and I develop a field to understand the application of field theory to particle physics means being able to reproduce such results. I think we more or less understand what's going on. I don't know if there is something that is bugging you.
What we did here is just analysis to understand or to predict the decay value.
To get a feel of what the numbers I didn't put, but even the numbers we can reasonably estimate. Notice that the muon will be very suppressed compared to the tau. Okay, that for example they have no color, so that I can just scale the masses. So tau is about 20 times heavier than the muon, so I should get a ratio about 400 between tau and the muon, which I think is true.
Okay.
If you look, sorry, Mahmoud.
But I mean, because you have coupling which are -1, so it's clear non-normalizable theory.
Well, no, because it's coming. It's not the coupling in the Lagrangian. I'm not allowed to write such couplings in the Lagrangian. The theory is not normalizable. But this is coming out of a loop. That, of course, anything can happen in out of loops. We will not only get dimension 4 interactions. Okay, that's okay. The theory starts at the 3 levels. The final results are summation of all the possible perturbative calculations. Okay, so don't be fooled by this demand. The rule says only good theories are normalizable theories, those in which there are no infinities in physical quantities. They have to be of dimension 4 or less. But it doesn't mean that you will not produce high-dimensional interaction. Of course you will. When we exchange the W boson, remember we get a Fermi interaction, which is dimension 6. We get it by exchanging the W boson in a low momentum. The thing is that it came from an interaction which has its own messenger. At the end, it may reduce to the effective theory. I'll give you more example along the lines. We are going to study a lot one other effective interaction, which is called Weinberg dimension 5 interaction, which gives neutrino mass. I will try then to once again, from now our understanding of the standard model, go back at the Fermi theory to see why that was an effective theory, could have been the full theory, and why it exchange of a heavy particle can produce that. But let's see if we understand this plot. How we are doing? Oh, here's that. Okay, what about the production? Let's try to produce the Higgs. Now, before we produce the Higgs at LHC, let's go back at lab. Let you and I try to understand why didn't they find the Higgs at lab?
What's in the
LEP. LEP, remember LEP? Large electron. LEP.
Oh, okay.
Sorry, I'll redefine it. Okay,
electron collider. Or
right.
or
Well, I'll go back.
Okay.
I'll go back and define it.
Okay.
I mean, I don't want you necessarily to remember. You know, there is an interesting thing the way you start. You start with Alexei, who gives you a feel of particle physics. Then I develop the formalism that should give us a way of looking back at the things that he said from a deeper perspective, in which we must, of course, get the same results. So let's try to. Is this clear, please? Can you think of a question? I'll have to erase this. I do wish the blackboard was big enough that I could keep. So let me make sure. I know when I'm not around, you may go around and say that there is a Fermion mass problem, but do me a favor, don't do it in my presence, okay? I'm going to try to ask you to obey, to have some respect, you know, for the statements that you make. This is a terrible language, and actually, just give me a feel. Go back to the history of physics and look at the situation where there was a problem. When there was a problem, there was a solution immediately. Actually, the solution often existed, but people were not aware of that. There are no problems that last for decades without no progress whatsoever. That usually means that there was no problem whatsoever. Because the thing is why asking me to say that there is a problem because I don't know why the numbers where they are, it's simply stupid. And I could prove it ad absurdum. I remember my friend Giyad Vali asked me this. He said I should publish this, you know, at least on April 1st. I said, look, assume that the numbers are what they are not. But that's stupid, you moron. Numbers have to be what they are. So this ad absurdum, you know, which is a well-known way of proving results, okay? There is no Fermion mass problem. Not only that there is no problem, I would claim that this is a beautiful dynamical theory of Fermion masses that allows us to test the Higgs mechanism in the gory detail. Imagine that we finally see that it goes that much in B, that much in tau, that much in muon, that much in strange, that much in... You're gonna love it. You're gonna believe in this profound thing that tells you that the origin of all masses comes from this one simple, incredible vacuum production. So let's go to LEP. Large Electron Proton Collider. In 1983, they found W and Z in what is called SPS in this large synchrotron. Okay, and they decided to dig a big machine that dig up a big tunnel at CERN. Okay, it's not at CERN actually. It's at the border between France and Switzerland. Goes under this little beautiful town when you walk in that green, nice countryside with cows and little towns around it. You would never dream that there is this incredible thing going on. Okay, and that's an EE bar machine which had a center of mass energy around. So let's say square root of S is around 200 GeV. I think it was 205 GeV, whatever. That was their energy limit. One of the reasons why it's easier, you know, there's always a debate, which machine should you and I build when you want to discover or do physics or whatever? It's going to be electron or proton machine. The advantage of electron machine you can see immediately. Well, it's clean. There are no these crazy quarks, partons as we call them, you know, the sea of them, which I sort of get a feeling what is going on. I remind you of the problems of understanding quarks, which we never see really. We sort of, or we see them in a funny manner, okay, we call scaling, deep inelastic. So this is a very clean machine. What's the disadvantage? Can you think of any disadvantage?
We cannot accelerate them very large energies.
The problem with the energy is because you have it has to do with the mass of the particle, the variation when you do a circular machine. But then there is a dilemma, should there be a linear machine or a circular machine? The linear dilemma is, the linear thing, some people argue can be good because then you don't have this energy loss of a particle going around the circle. But on the other hand, you are limited by the distance that you can have, whereas in a circular thing you can keep accelerating, guys, okay? There is another disadvantage of this machine. And notice what it is, that the energy is fixed. When I do the PP machine, I can confront it with LHC, which is a PP machine, or Tevatron, which is PP bar. I can also do PP bar machine, okay? This is called Tevatron. Anyway, LHC, why it doesn't matter so much? Because in the Proton, there are also anti-quarks. I can always find quarks and anti-quarks. Quantum physics. The advantage is when I fix the energy and I say that the square root of S here is, I don't know, 14 TeV, let's say, random number. Actually, that's the energy of the proton, but that's not the physical energy. The particles that are scattering, whose physics I have to understand, are the quarks inside. And their energies vary tremendously, right? There is a distribution of energy of these quarks. So I have all kinds of energies, and that's very useful when I have to make a discovery. Because I don't know at which energy the discovery will happen. So I have a lot of different energies. Because my quarks may carry 5 TeV energy or 2 TeV energy and 7 TeV energy, and that's good, I will see everywhere. Here I'm at one and the same energy. So typically people like these machines, when you already know your physics and now you want to study it in gory detail. So this is why in '83, when W and Z were found, they said, now we need a machine. They should see this guy, all these properties. I have to be sure that the standard model is correct. I need a factor of W and Z. And I will do the energy. I want to have sufficient energy to find W and Z. And study their properties, okay? And that seemed a reasonable number. You did what you could. Okay, now look at the irony that will happen, okay? This is really, life is not fair. Now, inside these people, there were guys that decided to look for the Higgs, and they devoted, many years of their life looking for Higgs. And this is a shame what happened. How can I produce it? Let's look at my plot. So that's the third. Well, the third line is something he plotted. This I took from Juadi, a review on the Higgs. I can actually send you this review. Send you the reference or send you the review. It's not a bad idea that you have this. It's a very comprehensive review which explains very little but collects everything. It's the most complete thing I have seen, but the physics, of course, we will have to understand by discussing or reading or whatever. So it says the first one is H nu bar. What will be the H nu bar in this machine? Can you guess? Oh, first thing. Why don't you just produce the Higgs? Why is he saying that the first thing is H nu bar? Why these neutrinos? Why not just Higgs? After all, E bar, Higgs, I produce it directly. Why is he not listing this at all? Notice that on the third plot, it's not there at all. Just Higgs. This is how you will produce the Z boson, by the way. How would you produce the Z boson? Why was this machine so good? Look, it was fantastic for the Z boson. E bar produced the Z boson, and then you study it. You can study its decays beautifully, right? You have one single well-defined Z boson. You can sit on its mass. You can do whatever you want. What's the problem here? The same way as the decay rate, also the production will be mf squared. mf or mw. This is 0. In order to produce some particle, you need couplings of order 1, like H coupling. Or maybe like alpha or order 10 to the minus 2, but not of 10 to the minus 10. M electron is 5 orders of magnitude lighter than W. Some people call this a fermion mass problem. They say, I consider this a problem. Why is fermion mass so much smaller than MW? I'll come and argue that this is not a problem. That's an interesting question. But it's not a problem. I will remind you of that when I discuss masses more deeply, because I'll have to study neutrino mass. I will have to ask why masses, some masses are small. All I know that I cannot produce the Higgs like this. This coupling is too small. This coupling is m electron over mw squared, and that's about 10 to the minus 10. So, what is h nu bar? Can you guess? Why I get nu bar? Well, I can look at this channel. E will become nu how? If it admits a W. E bar will become a nu bar if it emits a, so this guy will emit W minus going this way will emit W plus, so it's okay. Now look, this can produce the Higgs. And lo and behold, the machine has 200 GeV, Higgs makes 125 GeV. Ideal to see it. There is also another one, let's just see that there is HEE bar below that. Notice. How would I get HEE bar? By analogy with this. E bar, what is coming out here? Z. No, not the photon. Photon couples to the Higgs very little. I don't want that. I have to produce it. I'm not looking at some small branching ratio where I made like Higgs going into gamma gamma, even if it's a small branching ratio, because I will see these two photons and look at them. But I can't produce them. That coupling is too small, as we know. This is a little smaller, but both of them, and this is beautiful, this is clean, this is, you see an electron and so on. Now look at the separate diagram I give you. Plot. Look at the square root of S. So look at the WW. This is a W fusion, very often called WW, which is very important, which has enough energy. Look where the square root of S is around 200 GeV. This is for Higgs of 115 GeV, but 125 similar. What happens when the square root of S is 200 GeV? WW is negligible. The blue line is basically zero. There is one more. It says that I can produce ZH. How will I get that? EE bar. Remember what I said? I can produce Z. And then I can produce Z. And then I can produce H. I can get this. So look at the square root of S of 200 GeV, please. ZH dominates completely. The green one. The blue one is practically zero, right? Right, the green, the blue one, the green one is here, look, it's huge. And the blue one is somewhere here. It's much smaller. So, an incredible conspiracy. There were some people claiming that LHC should have gotten a Nobel Prize, which is crazy. How can you give 7,000 people a Nobel Prize? How could you distinguish that? But notice, the reason LHC saw the Higgs is because these guys were so unlucky. There was nothing new at the LHC. Their physics understood. All the things were, if you look at the Jardis review, this was computed long ago. We all knew how to look for the Higgs, okay? The thing is that they had enough energy to see this, but it's too small. The cross-section is small. You see, because unless this guy takes a lot of energy, you're suppressed by the energy exchange, okay? W is very heavy. So you can get rid of it if this guy carries a lot of energy. When it carries a lot of energy, you're using up a lot of energy, okay? At 500 GeV, if you look at the 500 GeV, that's the third plot, or look here at 500 GeV, the WW is dominant. So if the machine had been bigger, they would have seen the Higgs, the energy. But no, it's worse than that. This was very important. This dominates completely. But this guy has a mass of 90 GeV. This guy has a mass of 125. You need 250 GeV to produce the Higgs, but they had 205. Just lacked a little more energy. They even said at the end of the run, a few months before the end, that they see the Higgs at 115 GeV. That's why he made a plot. 114. And there was a serious dilemma for the director of CERN at the time, who was Luciano Maiani, I believe, having to decide, do you now let these people go on, or you switch to, it's the same tunnel that is used to switch to the LHC. It's the same huge tunnel of 27 kilometers. No, it's a monster. How physics evolved from tabletop experiments to, I remember when Tevatron was built. Tevatron is in Chicago, it's a PP bar machine. It's about 7, 8, 9 kilometers. I don't remember, I used to jog a lot, and I would run around, when I was visiting Fermilab, around the ring. I had a dream that I wanted to run a marathon, okay, but in order to run LHC, you have to be a marathon runner, basically. You know, marathon runners never run, they tell me, 42 kilometers during training. 25, 30 maybe. But, you know, that's a lot, 27 kilometers, okay, this monster. So I don't, this is really not fair. But there it is. Then it says that, what else he mentions that read me the third plot of the first of the three. There is H bar E, there is HZ, then there is H, notice that there is HTT bar. How would I get HTT bar in left? The third plot here on the production would be a left prime, would be a new collider that one hopes to build of 500 GeV, say, square root of energy. That would be a good machine to study the high precision properties of the Higgs. If you want to understand Higgs very well, you don't do the LHC because that's dirty. You have to build the electron positron machine. So how will I get Higgs EE bar, TT bar? Well, remember I can produce the Z, and Z can produce TT bar. Then, of course, once I have that, it's easy to produce the Higgs because Higgs couples a lot with the top quark. You can stack it here. So that's easy to produce. Then, and you pay the price. This is now a 3-body process in which you produce a heavy top quark, right? So H uni bar was also a 3-body process, but you had more energy. Phase space. Maybe some other factor which I don't see, but this is more or less it. Then there is also lithium HHZ. How will I get HHZ? Well, that's very subdominant, but it will be important. I just stack enough more Higgs. And I can stack it here, you agree? I can also, this is more interesting, I can stack it here. Why is this very important? Because this we want as a probe of the Higgs mechanism. We want to probe the couplings of the Higgs to itself. If the Higgs is really the guy that is responsible for all of this, I have to understand its interactions, because it's supposed to be the following. This is my potential. There are no G's, remember? There are no Wilson bosons, I've eaten them up. So I have interesting couplings here. I have lambda VH cube, and this is lambda VH cube. So I'm probing directly lambda V here. Okay, this is very important. Eventually, I maybe want to probe lambda H to the 4th and so on. Okay. So this is why you want to build this machine, to be able to study. Then you have also this interesting decays that you can probe, because this is now clean in the electron positron machine.
What about mu collators? Or they
Mu-mu collider, that's an interesting possibility. I don't know what will be built, okay? I wonder.
But it would be better with this kind of experiments.
Sorry? But it's a similar thing as this. Regarding the physics of for us, it's the same thing I have to produce. For you and me, that's more or less the same. Understanding this diagram wouldn't be changing. There are disadvantages. What is better to... I'm not the right person to ask for that. I have absolutely no idea what it... I wouldn't have, for example, gotten a debate. I would listen to them. I was working at Brookhaven National Lab. We were supposed to get the biggest machine at that time. That's an interesting story called Isabel. In late 70s, there was a great excitement. That's why I went to work there. After my postdoc at Maryland, I got a job offer from there were various places. I went to Brookhaven. It was very exciting, it seemed, because we were going to get this big machine. Now, to make these machines, you need superconducting magnets. At the time, people used to trust companies. So Brookhaven ordered these magnets from Westinghouse, which was a very important producer of this. And they all failed. You say that the magnets quench when they don't work, okay? And this is why sort of physicists decided they will never trust companies anymore. So what happens afterwards, physicists work together with the engineers. So the story of LEPO LHC is a great success of technology being built by physicists, okay? Among other things, as you know, internet arrived from LHC, the necessity of processing this data, okay, technology implications are enormous, okay, they're in every which manner. So the question whether it is useful to build colliders, obviously it is. It's crazy to argue that it may be a waste of time. Often people say the argument, oh, we'll find a new theory or not, that's, you never know. But as Glescher used to argue, you know, for us, colliders are like a hammer for a shoemaker. We cannot do anything without, it's true, and it's a nice analogy, okay? And the thing is, they don't even cost that much money. The only thing now is that you cannot build many of them, you can build maybe one, and that has to be a big international project. Unfortunately, it's very hard to get them, as you know. We are still not sure where, or even that will there be a new big collider. And that's a disaster, to go for a long time without experimental checks. I could say a few more words about the LHC, but let's leave that for Monday. LHC, and then I want to go again. You know, this was sort of showing you how a lot of this physics has to be done by discussing. One of the reasons that we which are products of developing countries, when I was studying in Yugoslavia, it was a kind of developing countries in my era. And typically in these environments, you learn more formal physics than actual phenomenology. It's much easier to do it. You see, I can follow formalism very easily, but in order to understand things like this, you need normally a cooperation, putting many things together, right, and the cooperation of many people. Have a look at it now that you see me argue. Try to understand the production to see whether it fits. The second plot, the LHC, it's kind of neat. Okay, I can just ask you on the one last, on the dominant one is the gluon fusion. Why is dominant? You and I will have to put the numbers, okay? That's not obvious. I'm not asking you to do that. Do you see what the bump is? Can you guess? Why does it get increased at some point? It goes down, there's a bump, and then goes down again. I'll leave you with this. With this thought. But where? Try to see it, watch.
This one.
Right, where is it happening? At what? Well, maybe it's not so obvious the way he scales it. It's not clear. It's not sort of linear.
It's 300?
Yeah, about 300-400. So, how would I produce the Higgs in a gluon fusion like this, right? I do the opposite. Right? It's the opposite from the decay. And you know why it dominates? Because it's not so much suppressed and there are a lot of gluons. Okay, so it's a good thing. At LHC there are a lot of gluons. And you don't pay the price to small coupling, so it turns out to dominate. Okay, I don't know if whether we can understand it, you and I, easily. But around 2 quark masses, you can produce them on shell. That's better. And then just radiate the Higgs. So that moment, you know, you go bump, and then, of course, with the energy, the cross-section goes down, because it just costs you more to produce the heavy Higgs with the Higgs mass. I'm sorry, not with the energy. The energy is fixed. The Higgs mass. Okay. What else? I don't know. Any question? I better stop. It's time to stop.